Let's do this example. So the question is, what are the three smallest thicknesses of a soap bubble that will produce constructive interference for red light with a wavelength of 650 nanometers? And like I said a moment ago, they say just take the index of refraction to be that of water. Okay, so a couple of things to note then about this setup is that in our picture, or in the diagram, N1 is air, right? The light wave's coming from air, and 2 is that soap film, and then N3 is actually also air. So N3 and N1 are both the index of refraction for air. It's basically 1. And N2 is the index of refraction of the soap bubble, or the soap film, which is very similar to water. So N1 is equal to N3 in that picture, which we're taking as just 1. N2 we're taking as basically the index of refraction of water. What that means in terms of the reflections is N1, when it reflects, is going to be inverted. Ray 1 is going to have that 180-degree phase change. N2, or sorry, not N1, the ray coming in, and then ray 1, reflected, inverted. When ray 2 goes down to the bottom of the thin film, reflects, the index of refraction outside or below is lower, so we don't get an inversion. So think about what that means for a second then. If N1, if the first light ray and the second light ray meet up, right? Forget about that distance t for a second. If they meet up, then they're going to be completely out of phase, right? Because the first one was inverted, the second one was not inverted, right? They're going to be off by half a wavelength from each other. So if we want them to be constructive, well, the distance that the ray 2 travels in the thin film, right, twice 2 times t, essentially, right, up, down and up, 2 times t, needs to be equal to some multiple of a half a wavelength. If it is, then when 2 exits, it will now be in phase again with wave 1. So 2t, we want to be some multiple of a half wavelength of this light. If that's the case, then we'll get constructive interference. All right, so what's the thinnest it can be? Well, in terms of our order here, the thinnest is going to be when m is 0, right? There's only one half wavelength difference. Essentially, 2t is equal to half a wavelength. But there is a complication, which I forgot to mention. It was on the last slide, actually. I'll just talk about it now. In that, when light goes from air to the soap, and when it changes between mediums, remember that light actually slows down, and that causes that affects the wavelength of the light too. So the wavelength will compress a little bit. So the wavelength of light in a medium, we generally would write with lambda sub m, indicating it's in some material that has an index of refraction. Very simply related though. It's just the index of, or the wavelength of light in the vacuum divided by the index of refraction of that light. So in A, we're talking about the light moving through the thin film. This wavelength, or the wavelength of the light there, is actually its wavelength in the medium. So the thickness for this film, the thinnest it could be to get constructive interference is just lambda over n, all that, move the 2 over 4, lambda over 4 n. Right. And putting some of those numbers in, over 4, and that index of refraction 3, get 122 nanometers. Very thin. Right, very thin. Right, so that's the smallest thickness, the first order sort of interference. The next smallest is going to be, well, when m is equal to 1. And you do the same sort of process, you end up, right, except for m being 1 there, end up with 366 nanometers. The third, when m is equal to 2, again, the same process, 610 nanometers. So, very thin films. And maybe we won't do all of B, but just to point out that in B, we're talking about destructive interference now, so the distance that N2 travels, right? Remember, if there was no distance there, then these ray 1 and ray 2 would be out of phase as it is, or they'd just be out of phase, so they would be deconstructively interfering. So if you want to keep them out of phase, right, the distance that second ray travels in the film, 2t, needs to be a multiple of the wavelength. That means it will have shifted any number of wavelengths, but whole wavelengths. So 2t would need to be a multiple of the wavelength. And the smallest thickness you can get to get destructive interference is sort of like what I was saying, where if t is essentially 0, right, there is no thickness to that. And if you put in m is 0 for this deconstructive formula here, that's what it tells you. T would come out to be 0. Which is not exactly physical, right? You don't really have a film if it has no thickness. So that smallest deconstructive interference is when the thickness is very thin, meaning very thin relative to the wavelength of the light. And you can easily get the next ones if you just plug in, m equals 1 will be the next smallest thickness to get destructive, m equals 2 will be the next. You can also get this thin film effect, like with the microscope slides, where you put something very small in between two pieces of glass, so that the gap in between the two pieces of glass is a very thin gap. And the diagram in B is showing, it's greatly exaggerated, obviously, well, hopefully it's obvious, but the glass is kind of tipped away from the other piece of glass, and so you have this air gap. And in this case, the air gap, that air is essentially acting as thin film air. So you can get these, well, you can kind of understand this pattern that you see in this situation by thinking of some light rays coming in towards the top of the glass, or the top of that top piece of glass, and say thinking about that first light ray on the left in figure B. That first light ray comes in, refracts, and then that refracted ray will reflect from the bottom side of the glass, bottom side of that glass, an air boundary, right? Bit of reflection, but some of it will refract and keep going. That will reflect on the bottom air to glass boundary, reflect, come back up. You get some other refraction, get one more refraction, but you get, in the end, you get these two light rays coming back from that same one light ray that came in. And say at that setup, or in that particular place, maybe the difference in distance of those light rays is traveling, along with the phase changes that might have happened for the reflections. Say they come back and they're constructively interfering. So that point right there, that light ray came in, constructive interference, and you see some light ray from 1 and 2 are going. But then you imagine moving a little bit from that first light ray over to the second one, right? And that air gap, the size of that gap is different. The distance that each is traveling is different. The difference in distance that they're traveling then is also different. And so you get this sort of thing happening where 1 and 2 coming out, but now they're not in phase anymore. Their phase is shifting a little bit, and you keep moving over and over and over. Eventually you get totally out of phase, 1 and 2, destructive interference, you don't get any light at all. You get this dark areas. Right? And then you keep moving along all the way towards like 1 prime and 1, 2. Eventually you move along far enough where the waves shift even more, they're back in phase, you see the light again. The picture has like a rainbow coloring, and if you use white light, or shine white light on this thing, then you'll see that. And it comes down to, again, the wavelength of the light is playing a big part here, so you get constructive and deconstructive patterns that are slightly different for the different colors because their wavelengths are different. So that's why you see this rainbow sort of thing. But if you do this and just shine a single color monochrome lamp, say like yellow light, then you just see these bright dark bands. And as the gap is kind of growing here. Or you're looking down on the top of the glass, right, and the gap is behind. It's an interesting application of this process, right, where there's gaps between these materials, air gaps, and you see these patterns forming. You get these interference patterns. One way that's used is to check the accuracy of lenses. In this case, right, there's actually two lenses that are convex on either side and then plane on the other side. So you're essentially making a lens that's flat and has this this curve that's perfect for what you want, right? But it needs to be perfectly flat on the other side. So what you do is you have, say, one that's like a standard, and it's as flat as you want it. It's exactly like you want it. You put the other one on it that you're trying to make flat, or you're trying to make that side exactly flat. When it's on there, if it's not perfectly flat, say it's like convex a little bit, then there's going to be air gaps there, right? And you'll get these interference from the light rays coming in, different angles going through different thicknesses, so like I showed you in the last slide, and you end up with these rings, which we call Newton's rings, even though Newton didn't really first get to them. Turns out Hooke did, but again, Newton was just kind of he explored them in great detail, don't get me wrong, but the name goes to him probably more because he was just such a big figure. Cool, so now you can kind of understand a little bit more, hopefully, why you see these crazy color patterns. Most of those pictures and situations, diagrams I was showing you are very uniform, very flat, even thicknesses, maybe a gradually increasing thickness. Nature's not like that, right? Nature is usually very uneven, varying thicknesses going on of a thin film. And so in some places the film is a little bit thicker, like this copper oxide film, a little bit thicker, so one color is actually going to be constructive there, other colors are not constructive there. Somewhere else it's a bit thinner, so different colors are constructive, right? So that's why you can get, just based on the thickness of that film and how that thickness varies, you get these crazy cool color patterns. The last thing we're going to talk about in this chapter is interferometers, specifically this what's known as a Michelson Interferometer, and it is a device that uses light interference of light waves, to make very precise measurements. The setup of the interferometer is fairly simple. Essentially, you start out with the light, this light source, S. It's going to make a beam sort of coherent light, usually like laser light, that maybe has been spread out a little bit. And that light is directed at this mirror, that half-silvered mirror, which is at this 45-degree angle. So when the light beam from the light source hits that half-silver mirror, the whole purpose of the half-silver mirror is like in comp shows, and you see a two-way mirror, those are like the half-silver mirror, right? So some of the light gets reflected back and it looks like a mirror, but the other half of that light actually goes through. So that's what happens here. Some of that light, some of that beam is reflected, right? Goes straight up. Some of it just goes straight through. So you get these, that sort of splits the beam into two. Some goes up, comes back down. Some of the other half goes across, comes back to the half-silver mirror. And when that top beam comes back down, some of it's going to go straight through the mirror. And when the beam from that second mirror on the side here comes back, some of it's going to get reflected down. So in the end, the whole picture is that light comes from the source, gets split, goes through these different mirrors, comes back, and is directed to the detector. Something to point out about this diagram, the angles from like C to A to C prime, right? That angle, it's there to show that there are actually two light rays, like there's one going up and one coming back, but those light rays are on top of each other. Same thing with C to B and then B to C. Again, they're just trying to exaggerate it, or not even exaggerate it, it's fabricated to show you that these are two light rays. In reality, those light rays are on top of each other. Thinking about interference then, if you have a single light source, split it in half, send it in different directions, they come back, meet up, right? They could be in phase, they could be out of phase, they could be in between, but it depends essentially on the distance that each of those light rays traveled after it was split. So if the distance to mirror 1 is the same as the distance to mirror 2, then when they come back, they will have all gone through the same amount of wavelengths. They'll meet back up again, they'll be in phase, and you'll get the light at the detector. You'll get bright light at the detector. If the difference between that path to M1 and the path to M2, if they differ by half a wavelength, or any multiple of half a wavelength, then when the light comes back, they're going to be completely out of phase, and you'll get destructive interference. You'll get dark. You won't get any light at the detector. This is all well and good. There's some complications, though, which we'll just talk about. This is a slightly more realistic picture of a Michelson interferometer. For one, the light rays going towards the mirror coming back are overlapping, as they actually are. But the other complication is that that half-silvered mirror has some thickness to it. And it's made up of some material. We've got a glass, usually, the silver on one side. So when those light rays go through that material, when they hit that silvered mirror, they're refracting, they're traveling through that material. If you look at the path for the red arrow on the right side here, right, the light that goes to the second mirror, M2, that light's going to hit the first mirror, refract, travel through that first mirror, and then it will keep going all the way to, or refract again, keep going to mirror 2, pretend that C is not there for a second. Keep going, hit mirror 2, come back. Right? So it will have gone through the half-silver mirror once. The blue ray, though, comes from the source, refracts, and it gets reflected. Right? So it actually goes through that thickness of the half-silver mirror once, twice, goes up to the mirror, comes back down, refracts, goes through one more time. So it goes through the half-silver mirror 3 times. So in practice, that path to M1 is always going to be seem a bit longer than to M2. So that's why you put in another piece of material in between the half-silver mirror and the M2 here, the other mirror, and that material is generally just cut from the exact same piece of glass that the half-silver mirror is, so that its thickness is the same, its index of refraction is the same. That way, the second light ray goes through it once, goes through it twice, and now both light rays have gone through that same thickness, so that same material, 3 times. So in that setup, now if the distance from our silvered mirror to half-silvered mirror to M1 is the same as mirror 2, we're all good. Right? Accounted for all of that refraction and index of refraction and so on. There's one other thing that you might think of as a complication, which, well, probably not, I'm just going to mention it anyway though, is that when you have reflections, you might have inversions, right? When the material that you're reflecting off of has a higher index of refraction, then you get an inversion, or a phase change, a 180-degree phase change in that reflected ray. Nicely enough, it turns out that both of these rays experience 2 180-degree phase shifts, so it's equal change there. We don't have to worry about that reflection, or the inversions to reflection. I said all that stuff in words, but basically, if I put that into an equation, the condition for in-phase light to get to the detector, or to get to the eye, pictured here, is when the path length difference, D1 and D2, is any multiple of a wavelength, meaning that if they're phase shifted from each other, they've phase shifted all the way to being in phase again. At least 1 wavelength, 2 wavelengths, 3 wavelengths, right? Any number of them, they're back in phase. For out of phase or deconstructive interference, you need that path length difference to be any multiple of a half wavelength. This interferometer, this Michelson interferometer, can be used to make very precise measurements. Well, in the previous picture, here you might have seen that on the diagram, one of those mirrors is labeled as movable, one is fixed. So we have one mirror that's fixed, and I can adjust the distance to mirror 1, and by adjusting it, I'm changing the difference in the path lengths. So I can do these fine movements in mirror 1, and I can go, that essentially will take me from constructive to deconstructive and back again. In practice, when you look at this, it's not just, a single bright spot or a single dark spot. The light that's traveling through this interferometer is, in a sense, sort of spread out And being spread out, it will have gone different distances depending on which path length it took. So in practice, what you would see in these interferometers are actually like a bright or a dark central spot, and then rings of bright and dark spot, or rings of bright and dark around that. In this nice little GIF here, they're showing these very slight, small adjustments in the placement of mirror 1, right, that movable mirror, adjusting by 0.01 millimeters, very, very small, right? And when you do that, you're moving that mirror away, right? You're adjusting the phase between these light rays that are recombining, and that ends up causing your pattern to shift in such a way that the rings will sort of like move out or move in. Right? Those rings are concentric sort of constructive and destructive interference rings, depending on the distances that the light rays are traveling. And what you can do is if you adjust the distance to that movable mirror by sort of moving the mirror slightly away or moving it towards, then the distances that these light rays are going is changing, and what happens is these patterns, the rings, concentric rings, just start to either expand or contract, and one ring will replace where the ring before it was, or et cetera, et cetera. And if you think about it, what's happening there is you're shifting the distance that one of the light rays is traveling, right? So you're adding more, well, if you're pulling the mirror away, you're adding more wavelengths that ray will have gone through versus the other one. And you have this thing where they start out maybe constructive, and you have this one of those bright rings, and you pull the mirror away, the light ray to the moving mirror, it'll go through a little bit further distance, and so its phase will shift relative to the second wave when it recombines, and they'll start to be out of phase. And you keep moving that mirror back, eventually you shift enough that it's got a full wavelength difference, and now you're back to in phase again. So think about it, moving that mirror back a little bit, right? Say that's the delta D is the distance of that mirror moved back. The light ray, the distance of the light ray it's traveling is actually that difference times 2, right? Because it goes to the mirror and it comes back. So if I want the light ray to have traveled a full extra wavelength, that means I will have wanted the mirror to move half a wavelength. And any multiple of half wavelengths the mirror moves, that ray will have traveled an extra whole wavelength. So that's why you end up with this relation where the change in the distance to that movable mirror is equal to the multiple of half wavelengths. In this case, m is not the order of interference. M is the number of times that a ring sort of moves from one place to another. So if you watch one spot on this GIF, right, this is the person moving that mirror slightly, right? And so watch one place, the m is the number of fringes, bright fringes that will have passed that point. So it's one fringe pass, right? That's one extra wavelength that the wave traveled through. Another one passes, that's another wavelength. Right? So you can measure these very small changes in the amount that that second mirror, or the movable mirror, is adjusting. So a quick example to illustrate how small we're talking about again here. If you have a red laser, wavelength 630 nanometers, it's used in this Michelson Interferometer, keeping the one mirror fixed, the other mirror is moving. You're looking at the fringes, right, these bright constructed rings, and you find the distance the mirror is moved for one single fringe to move past that reference point, right? So for one constructive ring to have moved out to its neighboring spot. Try that again. So use that relationship we just talked about. And there's only one fringe that moved past this point, so we'll say m is 1. And O just to indicate this is the wavelength of this light in a vacuum, as opposed to thinking about it in any of these materials. Putting those numbers in, pretty straightforward. Well, just half of that. 315 nanometers. Tiny little change in that mirror distance. Those are very small changes. Let's look at one more example just to illustrate some of the usefulness of this interferometer. So a lot going on here, but essentially you have an interferometer, and there's a chamber in one of the arms. At first, that chamber is empty, and then you fill that chamber up with. Slowly, you fill that chamber up with a gas, and you want to know what the index of refraction of that gas is. Right? If you're using this interferometer, you're going to be able to measure the index of refraction of the gas. So when it's empty, these two paths are the same. Well, we'll still get that same sort of picture that we had before, all these concentric rings. But as you fill up the chamber with gas, you're in effect adding more wavelengths. Right? So in the gas, the light slows down a little bit, the wavelength shrinks just a tiny bit. Right? So we actually fit slightly more wavelengths in that 2 centimeter width than it would have been without the gas. So the effect of that is to start to phase shift the one ray from the other ray. So we start to shift them off from each other, and as we fill up the tank, we're slowly filling up that little vessel with gas so that the index of refraction in that little tank is increasing from air to whatever it is in the gas. And that's why the fringes are going to just start moving past each other, because the one ray is it's getting phase shifted essentially. There's more wavelengths that are happening in one of the arms. So if we watch it, right, as we fill it up, this little tank up with gas, as you're watching the combined rays again, say you see 122 fringes pass by, right? So watching that fringe pattern, you have a little spot ticked off, you see 122 constructive rings pass by. The wavelength of the light was 632.8 nanometers. What is the index of refraction of that gas? So recall that in that medium, the wavelength of light is actually its wavelength in the vacuum divided by the index of refraction of that gas. So I do this slightly differently than the book goes about it, but we'll get there. The way I would think of it is that if you imagine no gas is there, then there's a certain amount of wavelengths that fit in that 2 centimeters. So this is the number of wavelengths that fit in 2 centimeters. And instead of writing that 2 centimeters all the time, we're going to call the width of that chamber T. So the number of wavelengths that fit in there is 2T, right? The wave's going to go one way and the other way. That distance divided by the wavelength in the light. And so without the gas in the chamber, it's just the wavelength of the light in the vacuum. So no gas, with the gas, how many wavelengths can it fit in there? Well, it's still that distance, but now it's divided by the wavelength of light in the gas. Then the difference in those numbers is the amount of wavelengths that have been added to this second path, right, or the path that goes through the tank. So another way to say that is that difference is actually the 122 fringes that we would see. Right? That's the shifting of the phases between those. They shift 122 times, 122 wavelengths there. And then just writing out what those were and doing a little bit of algebra here. Oh. Let's leave it like that for a second and be clear that lambda n is lambda over n. Right. Get that. Remember that was equal to that 122 fringes, and what we're interested in is n. Turns out that it's very close to 1, so it's good to just keep the 1 by itself and see what that difference is from 1. Plug in some of these numbers. Minus 2. Got to put it all in the same unit. Might as well do meters. Remember, T was the width of our chamber, 2 centimeters. Turns out that's 1 minus 1.93 times 10 to the minus 3. No more units there, those meters cancel out. So the wavelength, or sorry, not the wavelength, the index of refraction of this gas, 1.0019, which in practice is very, very close to the wavelength, or the index of refraction for air. The fact that we could measure this with our interferometer shows the sort of the effectiveness of that interferometer. In other cases, previously, we maybe would have measured the index of refraction of a material by how much light refracts through it, right? By seeing how much light ray would bend, we could have measured, you did that in the lab, found out the index of refraction of that material. But this is so close to air, you would never be able to do that measurement with refraction alone. You need interference, and this interferometer makes that possible. And finally, that brings us to the last slide, which is a different version, or not even another kind. It's an interferometer. You might have heard the detection of gravity waves, which first came out a couple years ago at this point. But it was by this experiment called LIGO, which is a Michelson interferometer. Essentially, there's some fancier things added to it, but that's the basic bones of it, is an interferometer. It is enormous though, as far as interferometers. Usually interferometer, like the pictures that we're going, the diagrams, ones we're thinking of, like a meter, 2 meters. LIGO is an interferometer where the arms are kilometers, miles long. Basically, the longer the arm of the interferometer, the more sensitive your measurement can be of the change in distances between those two arm lengths. Yeah, so LIGO is measuring the change in, or distortion of space-time itself. It turns out that when you have two black holes that are orbiting each other and then merge, the black hole itself already they warp space-time ridiculously. But when they merge, it is like dropping a rock into the pond, but it's no longer a rock, it's these two black holes, and the pond surface is space-time. And so the two black holes merging sends out these ripples through the fabric of space. Gravity, the force of gravity, is actually a very weak force compared to the other forces. And what that translates to here is those waves are extremely tiny in a sense. They're very, very faint and very hard to detect. So LIGO uses this interferometer, this massive interferometer with a couple of additional properties to even enhance its sensitivity more in order to measure these extremely fine changes in the fabric of space-time. So when a ripple from this merging of black holes happens, the ripples eventually travel to Earth, and since these arms are at right angles to each other, generally the ripples are going to affect one arm slightly differently than the other arm. So when the gravity ripples come, there's a little bit of change, and that affects what's happening at the detector. So the other examples I showed you, right, we're measuring distances that are like changes in that distance to the second mirror. It's like nanometers, hundreds of nanometers, really small distances. LIGO, though, takes it to like a whole new level. They can measure a change or detect a change in distance, the distances of these arms or the lengths of these arms. They can measure a change to within 1/10,000th the width of a proton. It's like crazy. This is actually from their website. It's a wild way to put it. The sensitivity that they have with this interferometer is essentially like measuring the distance to the nearest star, which is, what is that, 4.2 light years, or something like 25 billion miles away. Measuring that distance to an accuracy within the width of a human hair. Like, that's as sensitive as this thing is measuring. Mind-boggling. Very cool, though. They've detected a couple of gravity waves at this point, actually. Very nice confirmation of general relativity. Excellent. That brings us to the end of interference, chapter on interference. Excellent. Have a good one.